Good afternoon, everyone. My name is Bruce Momgen. I am one of the Postgres core team members. I've been working with Postgres for 20 years, and I've been working with Enterprise DB for 10 years. Enterprise DB obviously provides enterprise tooling and support and services around Postgres, and I've been enjoying my time there. 10 years is a long time, but I still enjoy it. I am from Pennsylvania. I travel to about 30 conferences a year. And when I'm not traveling, I'm home. So I don't go to an office, like I work from home. So I've been doing this traveling at this level for about 10 years. Probably travel about 90 days a year, and then 270 days I'm home. So it's not bad. And I like traveling, so it actually works out really well. And a lot of my children get to come with me. So I was just in Moscow in Estonia a week ago. In about 2 weeks, I'll be going to Japan and South Korea for a conference, and then I'll be home for a while. So it's a lot of fun. I get to meet a lot of Postgres people and hear what they're doing. And obviously, I have a lot of presentations, so I'm usually giving presentations at these conferences. And I enjoy it very much. I used to be a high school teacher, so if you feel like you're in high school, kind of a little bit, sorry about that. My presentations are actually right here. If you want to look at this presentation now or in the future, you can just go to that URL and pull it up. In fact, there's 30 presentations there, a lot of them with videos. So if you're really gung-ho Postgres and you want to kind of spend a day sort of listening about Postgres and everything. Sometimes you pull the slides up, you listen to the audio. It's actually kind of cool. I've done that for some other topics that I wanted to learn, and actually it works out really well. So again, that's where the presentations are. This presentation is a very generic presentation. I enjoy giving it because I think it sort of forces people to look at databases a little differently than they had been maybe in the past. And it's pretty generic. I mean, it's not even really Postgres specific. A lot of the things that I'm going to talk about are pretty true of all the relational database systems, to some extent even true of some of the non-relational databases. But obviously, I'm going to be focusing on Postgres. I'll talk about some of the specifics. But my real goal here is to give you a new way of thinking about database performance. I think in a pretty interesting way. Obviously, I talk about this a lot. I give one-week training classes every quarter to Enterprise DB customers and so forth. So, obviously, I've been doing this for a long while. The reason I developed this talk is because when you're looking at database performance, there's really 3 levels that you need to look at. There's the hardware level, there's the tuning of the database level, and then the SQL query level. To me, there's 3 kind of levels so it's hardware, database server tuning, and then SQL queries, right? And I'm going to talk just about that first layer, because if you don't have that first layer right, it really doesn't, you can only get so far with the other 2 layers, okay? And I've seen a lot of people not understanding the database layer, kind of coming maybe not as database seasoned people and saying, oh, this is just like every other thing I do. I'm just going to, I'm not going to learn. I don't think the database is anything special. I'm just going to basically treat it like any other piece of hardware. And the fact is, you really can't do that. So what I really want to get across is how databases are unique in a lot of ways in their hardware requirements, and give you some sort of ammunition in terms of how you need to sort of set things up and talk to your infrastructure team when they're setting up a database server. So you would think this is my outline. If any of you have ever sort of thought about database hardware, and I have to admit, most people, when they're thinking about database hardware, are hearkening back to the time where they can play computer games. I kid you not, but usually when somebody's thinking about their hardware, they're sort of thinking of like refresh rates, and I'm not trying to belittle it, but a lot of people's first experience with high-end hardware is gaming. nothing wrong with that. I got 3 boys and a daughter, and I can tell you for sure that's the way it is, right? But when you're going to a database, actually these are not really the things you should be focusing on. And that's kind of a mind change, because again, you introduce to databases, usually gaming is the high-end sort of thing, and you're thinking of all these things, okay? But they're actually not the things you should be thinking about, particularly when you're talking about a database. And I'm going to explain why, and I'm going to go into specifics, okay? To actually go into exact cases why I think this is true. And also, I can take questions, so I'm going to stop whenever somebody wants to ask a question or whatever. You want to raise your hand, or I'll stop and ask for questions. We certainly have plenty of time. I only have 26 slides, so I'll be good. Usually it's nice to ask questions because you get some feedback and, it kind of some dialogue sort of as I go through this, okay? So this is the way you typically think of a server, okay? Again, harking a little back to gaming, but also a lot of other applications have this kind of setup, where the CPU is sort of thought of as the most important bottleneck in my machine, in my system, and that's really where I want to put the majority of my expend, okay? So if I'm going to spec out a server, I'm probably thinking that red level first. And then I might be thinking about the memory level, okay? And I/O really doesn't enter into it a lot. It enters into it in terms of capacity, but capacity is not an I/O parameter. Capacity is an operational parameter. It's not you don't think, the amount of, the size of your storage does not really represent your performance in a lot of ways, okay? And that's usually the way people think of it. And what I'm basically going to hammer home through this presentation is that this is the way you should be thinking of a database server, okay? The CPU, as you can see, has shrunk, okay? It's actually the last thing we worry about. In fact, in this presentation, it's going to be the last thing I talk about, okay? The I/O becomes this hugely important thing that, really normally doesn't appear as a performance issue, but for databases it does, and I'm going to explain why, okay? And then memory, and then CPU kind of comes in. I'm not saying the CPUs are unimportant. You have to have the CPUs, right? But they're not the kind of performance critical case that you have with a normal computer or a normal use of a computer in your organization. I'm going to specifically explain why, okay? So why is it different? I'm going to take questions in a couple of minutes. Why is it different? Why do we have to think of things this way? And the reason is because traditional use of computers within an enterprise typically follow this kind of workload. Now, obviously, this is a very contrived example, but in general, this is kind of what people are doing, okay? They're doing web traffic, so they're doing huge amounts of network traffic, right? They're doing text processing of some type. They're running virtual machines, and they're running application servers, running application code. Okay, they're running Java virtual machines, they're running scripting languages. All these things are huge consumers of CPU, okay? They have a very CPU-heavy sort of component to what they do, okay? I mean, like when I think of network overhead or virtual machines, or the I/O part is not really, doesn't really enter into it. Yeah, there's got to be an I/O part, because when you shut the application, you got to permanently store it some way, but it's not sort of considered to be endemic into what that particular thing, what that particular use case is. But with databases, it really is different, okay? Databases are you're going through huge amounts of data. That's almost like by definition what they do. You're doing huge sequential scans of your data. You're doing a lot of random I/O, which very few applications do outside a database. I mean, how many applications really are doing random I/O within a file, right? I mean, not many, except the database, which does it all the time, right? So all of a sudden, you've got really an I/O usage that's really atypical, which again starts to explain why that I/O area becomes so important. You have unpredictable query requirements. So usually if you think of a web server or an email server or application server, the load is pretty, it's pretty much running over the same code all the time. And, okay, you have 70 users, okay, you have 90 users, but kind of the use case is kind of the same. But database is like completely, somebody fires off a huge financial report, and you got this huge amount of random usage that you typically, again, you don't have, network traffic doesn't usually come in a huge sort of bursty like craziness in the same way. It has some burstiness, but I would say databases even have more. And then reporting, you're running huge reports, churning through huge amounts of data. And the bottom line is that these are not heavy CPU processes. These are really relying on the I/O subsystem in a lot of ways. In a lot of ways, your system is going to be throttled by that I/O. And by corollary, your system is going to be throttled by the spend you put on I/O. And that's what really drove me to write this presentation, because I used to see people speccing out systems, and they would post to the email list. Now, I'm not singling out any individual, but you see this all the time. They'll say, we have a Postgres performance list, and they'd say, I'm speccing out a new server. Here's what I'm thinking of. And you know exactly what that spec looks like. It's like, okay, I got 8 sockets, and each socket has 6, and it's this gigahertz on this one, and then I got this much RAM. They don't mention if the RAM's ECC usually, which I'll talk about in a minute. I'll get to that. I'm not going to miss that. And then the I/O thing, it's like, oh, it's RAID 5. I'm also going to talk about that. I don't want to hide, but and they're like, well, this many RAIDs, and it's this, and I'm like, and we basically have to kind of go in. Whoa, hold on. I don't really want to hear more details about CPU. I want to hear about your I/O subsystem, because that's really where things are going to be happening. That's where you're going to bottleneck is going to be. So what breaks my heart is to see huge spend in servers put into the CPUs and insufficient spend put into the I/O subsystem. And I don't know how many of you do production monitoring of your database servers, but when you do a top or HTOP on a database server, like the load average is like what? 0.1, 0.2 maybe? Like I don't see a lot of huge load averages. There are some cases I'll talk about later, but in general, database systems are often not throttled by their CPU. Now there are some specific cases they are. I'll talk about that. But in general, you've got to think of that whole stack together, not having the I/O system be sort of an afterthought, which unfortunately I think a lot of times happens because people are speccing out servers with this assumption when they should be speccing them out with that assumption. So with that sort of introduction, I just want to stop and take questions that people have. Okay, I'll take that as good, I guess. So let's dig in here. And again, this is very Postgres specific, but again, any relational system has a very similar sort of use of storage and requirements. And what I'm going to highlight from this presentation, this slide is to me sort of the Rosetta Stone of understanding how Postgres handles things like checkpoints, the write-ahead log, crash recovery, all this kind of stuff. And I'm going to walk you through it, but what I'm really going to be highlighting is the idea of how that database is using the storage and the requirements the database has on that storage that are unique to databases, okay? So let's take a look at this slide. We got the 3 at the top. We got the 3 Postgres processes. So we're assuming we have 3 running sessions going, okay? And in red here, we have the shared buffer cache. And that's where all of the reading and writing happens. So every time we need to write to the database server, we're going to write to that write-ahead log, to that shared buffer cache. Anytime we're going to read something, we're going to read it from the shared buffer cache. If it isn't in the shared buffer cache, we're going to have to go to the kernel. So the kernel cache is kind of sitting under there. And if it isn't here and I need it, I'm going to ask for it here. If it's here, it'll get transferred right up into the shared buffer cache. If it's not here as well, I have to go to disk. So there's where my I/O is going to happen. Okay? comes up into the kernel, kernel sends it up into the shared buffer cache, and then these sessions can start working with it. Okay? So you can kind of see you basically have 3 layers of, like kind of 3 stages kind of going down. You've got the shared memory, shared buffer cache, which is a fixed size. You've got the kernel buffer cache, which is a variable size depending on how much free memory there is on the system. And then you've got the disk blocks. And I can go into the philosophical reason of why the shared buffer cache is there, why the kernel cache is useful. It has to do with elasticity of workloads. There is an overhead to having that secondary cache underneath there, but there are a lot of advantages. And again, it's a philosophical issue. If people are really interested, we can go into it. But right now, I'm not going to. So what happens when you want to change something in the shared buffer cache? How do we make that durable? As you know, all of the relational databases are ACID compliant. The D in ACID represents durability. So how do we make something durable when you commit a transaction? How do we guarantee that that's permanently stored? The way we do it is every time we change something in the shared buffer cache, we also append a record to something called the write-ahead log. If you've seen the PGX log directory, that's what that is. It's a bunch of 16 meg files, and you're always appending to these 16 meg files, basically. But appending to the file is not enough. Because of durability, we have to put that data in a location, so if we lose power or the operating system crashes, the data is permanently stored. So what we normally do is we issue a fsync call at the end of every commit, and we flush the write-ahead log to the kernel disk buffer cache. Okay? And because the kernel disk buffer cache is also in RAM, we have to issue an fsync call and get that to some kind of permanent storage. And I'm going to go into a detail of what that permanent storage looks like, but you kind of get the idea. Okay? When crash recovery happens, when the server starts up, it realizes it hasn't shut down cleanly. It'll look at the end of the write-ahead log. If there's no shutdown record, it'll start reading the write-ahead log from the last checkpoint and basically replay those into a special recovery process, which will apply the changes to write-ahead log and then issue checkpoints to flush the data down to disk. I'm not going to get into what a checkpoint is. Checkpoint effectively is taking all the shared buffer cache pages that are dirty, f-syncing them to disk, and then recycling the write-ahead logs effectively. Okay? But that's not super important to what we're talking about. What is important is you've got this continual requirement to be f-syncing. Okay? You've got this continual requirement that you're always flushing things down to disk. I'm going to actually do something kind of unusual today, but I'm thinking, hey, I like unusual. Okay, so I'm going to make this super big, and I'm going to show you something, because people like to see stuff. I think, anyway. Okay. So no, I don't want that. Thank you. Yeah, as soon as you open that, and everyone shows up. Sorry. Let me be a nice person here and shut everyone up here. Okay. So if I do PG test fsync, which is a tool that you get supplied with Postgres. In fact, Peter Eisentraut is the one who moved it into bin, so it's installed by default now. If I run PG test fsync, which is going to run fsync over and over again on an SSD, okay, I'm getting pretty good performance. I'm getting roughly 6,000 fsyncs a second, okay? And that's pretty good. It's on SSD. I'll explain why that's useful. But that's pretty good. Now, if I go over to another drive, which happens to be a magnetic drive, which has the drive cache turned off for reasons I'll explain in a minute. Look at that number when it comes up. 80. Okay? Ouch. What that is effectively telling me is I can commit 80 transactions a second. Now, Postgres has the ability to piggyback commits together, so I'm not saying it's like kind of stuck at 80, but there's serious throttling going on here, okay? I don't care how many gigahertz your CPUs have, you're going to be suffering if you can only, look at this. Oh my goodness, look at this. This is down to 11 here. I mean, this is suffering, right? You've got a machine that's supposed to be really fast, and because I'm running on magnetic disk that doesn't have a cache, because the cache isn't durable, I had to turn that off, okay? I've got effectively a tremendously bad system. And the way I did it is if you look at the etsy HD parm file, which is right here, okay? Etsy HD parm, I have one SSD. That SSD has a battery, which I'll explain in a minute. I can turn the cache on for that drive because it has a battery. But all these other ones, which admittedly are cheap disks. These are Western Digital 5400 RPM green caviar drives. Okay, they're archive drives. They're consumer archive drives. But this is what you have to do if you want your system to be durable. Okay. But when you turn that cache off to be durable, you're looking at 80 commits you're looking at 80 F-syncs a second at best. Okay? That's the kind of reality check that caused me to kind of write this presentation. Now, it's not super terrible because there are ways around this. Okay? So this is the traditional stack that you see. Okay, where you have the write-ahead log. Remember, this is the same stack we just saw, right? We've got the shared buffer cache. I just stripped it off. I just took this piece and I stripped it off. So I opened this piece up between here and here. Okay, so you got the shared buffer cache up there. You got the write-ahead log, and you got your kernel disk. But again, when you do that F-sync, because Postgres needs to be durable, we need to send it to the kernel buffer cache. We then need to send it to the HBA. The host bus adapter, which interfaces between your computer and your drives. Then it has to go to the disk cache, but because this is a magnetic disk, there's no battery on that cache. That battery, if I lose power, that cache is going to go away. It's not going to be written to the drive. Okay, in 99% of regular drives, there's no battery on a magnetic disk's cache. And therefore, you need to turn that cache off in HD parm so that your system's durable. If you don't do that and you crash, you're going to corrupt your database. So it's not an option. And then you send it to magnetic disk. Okay? And this is just terrible performance. Now, there are some ways around it. And fortunately, if you think about it and you put a moderate amount of money, you can avoid this kind of throttling of your database. And again, I think that's very important. One easy way to do that is to have a battery on your HBA or on your RAID controller, okay? Batteries typically maybe $200, $300, right? Please put a battery on before you buy more CPUs, right? Because I just kind of explained, it doesn't matter how fast your CPUs are if you're having that F-sync problem. So what happens when you have the battery is the data can be F-synced to the kernel F-syncs it to the HBA, and the HBA can respond right back and say, that's durable, I'm done, I'm acknowledging that F-sync. Then at some point, at some later time, the HBA can send it down to the drive. Okay, and again, if you lose power, the HBA, the battery is keeping that HBA's cache valid. When you power it up, it's going through the same process. It's going to write it down to the disk. Okay? Going a little farther, if you have an SSD, which has become super popular for very good reasons, okay? Any good SSD is going to have a battery on it, okay? In fact, I'll go so far to say is if your SSD does not have a battery, do not use it for a database. Because the cache on an SSD is more than just a cache. It's actually a staging area because SSDs require roughly 128K writes. So it's more than caching the data. It's actually staging it and writing these 128K pieces to the SSD, to the NAND. Okay? So if you don't have a battery here, then effectively your system, you can't turn this cache off because you'll burn out your SSD because every Every time you write 2 bytes, it'll be writing 128K to your NAND. Right? That is not going to work very long. So in a lot of cases, either if you turn it off, it'll burn out your SSD, or it'll just ignore the fact you turned the cache off, and it'll still use the cache. Okay? So the bottom line is, if you want to use an SSD to play games, fine. The games do not have a durability requirement. Word processors don't have a durability requirement. Databases have a durability, relational databases have a durability requirement. Okay? And if you don't durably write this data, you will corrupt your database in short order when you bring it back up. Okay? We actually have a tool in the documentation called, what is it, fsynctester.pl or something like that. It's in the docs. And actually, it's a little tool that allows you to test if your storage is durable. You run one Perl program on one computer, you run another Perl program on the computer that's being tested, and you pull the plug. You pull the power as it's testing, and then you plug it back in again. And then the monitor Perl program will tell you if all the data it thought was written was actually written. Really a nice, I think it's called diskchecker.pl. There's a link in the URL that actually tells you how to get there. But again, this is not an optional thing. This battery has got to be here. And when SSDs came out, and I was like, oh, wonderful, it's going to be wonderful. Random I/O is great, yeah. Great throughput, yeah. Great concurrency, yeah. But there was a lot of people who corrupted their systems because they didn't understand this battery requirement. Going sort of really to the end of performance is the flash-based systems. Typically, this would be Fusion I/O is the best known name for this. And it's basically just DRAM with an interface that makes it look like disk. Okay? And those always have a battery, because if they didn't have a battery, the DRAM would just erase as soon as you lost power. So by definition, they have a battery. And again, if you have something with a battery, either here or here, you may not need a battery on your HBA. Like, for example, on my server at home, I don't really need a battery. I already have a battery on my SSD. I don't need another battery on the HBA because there's already a battery kind of down in the stack that prevents me from having to wait to get the data to get down to durable storage. Okay? Any questions? Okay, all right. So just some terms as we kind of go through here. Write back versus write through caching. Write back means the write is acknowledged right away. Write through means that we write it to the lower layer and we wait for the lower layer to acknowledge. So that sort of cache stack that you normally have, for example, here you've got a cache here, you got a cache here, you got a cache here. A write back would be basically as soon as it receives it, because there's a battery, acknowledge it right away. If there's no battery, it needs to send it down until it gets to its durable area. That layer can do a write back. Okay? Again, there's different layers that we can have here. And again, you can control the write back versus write through characteristics of your drive in the HD PARM file. And I recommend you do that as database administrators. Figure out which of your storage systems are durable. You can leave the cache on there. You have to turn the cache off for those ones where they're not, particularly the cheap magnetic disks that I happen to have on my server for archiving. Okay? Again, the HBA is very nice. It's one place. You put the battery in one place. Magnetic disk, again, getting into some details here. I'm sorry, let me, did I talk about? Yeah, okay. So magnetic disk, RAID 5, RAID 6, probably try and stay away from it, please. It's not really great for databases. If you're storing Word documents, RAID 6 is fine. RAID 5 is fine. Okay? But databases just do too much writing, and databases will write and they'll wait for a reply. Almost no application does that. When you hit send in LibreOffice, it isn't waiting to get an acknowledgement from the drive. Okay? It's throwing into the kernel, and it's waiting for the kernel eventually is going to throw it out. Okay? But databases are always going to wait for that acknowledgement because they have that durability requirement. When you're doing RAID 5 or RAID 6, you're writing to 2 or 3 drives for every fsync. So not only is it bad, but it's 3 times as bad. Okay? Just stay away. RAID 10, everyone loves. Databases, everyone loves RAID 10. RAID 10 is striping and mirroring. I know it's more expensive, but RAID 5 or 6 is just really slow. Make sure, obviously, if you're doing magnetic disk, the more spindles, the better. Another thing that a lot of people miss, how many people know what SMART is? SMART? Good, good. For those of you who don't know, SMART is a tool that will run on your server and will check the health of your storage devices. Doesn't that sound like a good idea? It is. Because what happens is that a lot of storage devices, not only magnetic but SSDs, will actually report how well your system is running. SSDs, for example, will show you what your wear indicator is. Okay? Usually when a magnetic disk, before a magnetic disk dies, probably for hours before it starts throwing warnings of retries and stuff like that. If you don't have SMART running, it's called SMART D. If you don't have SMART D running, you're clueless. As an administrator, you have no idea what's going on until the server stops running or your database server is hung up because your storage is dead. But normally there's sort of a warning of death. And what SMART D does is it gives you that warning so you can be proactive. You can be like, oh, sounds like there's a problem. Let me swap another drive in there. Okay, instead of waiting for catastrophe. I can run SMART D. I run SMART D, but I can also run Smart CTL. So so we say Smart CTL-A dev SD. There we go. So that's the SMART report for my SSD, and it tells me the type of drive, Intel, and it shows me a whole bunch of information about it. Right here you can say, here's the wear out indicator right here. I'm not sure how many of you saw Peter Gagin's talk. How many of you were in Peter's talk, the hash versus sort? Yeah, so he's responsible for this 94 number because he was working on a patch that he ran on my server for like a week. And I used to have like 99 wear, and he kind of knocked it down a little bit. He may not even know that, but it's kind of funny. But anyway, if that number gets low, I'm going to get a warning. Okay. Same thing with if I do it on my magnetic disks, right? This is the Western Digital Green Caviar. And again, I'm getting information about temperature, power cycles, different errors that I'm getting. I can run self-tests on it. I mean, this is gold for administrator. Yeah, and again, there's Smart D, which will basically monitor your system all the time and tell you when something unusual is happening. Again, if you're buying magnetic, try not to get a consumer drive. I admit I'm using consumer drives, but not for databases. I'm using it for archiving of videos and family photos, and I've got 4 of them that are in different places in the world, basically. So again, just be aware not to get something that's too cheap, because when storage goes bad, bad things happen to databases, as you know. SSDs, again, I've gone over this. There is a staging area there. It's not just a cache. Be aware of that. If you turn off the cache, you're gonna burn it out. Here's there are some kind of performance recommendations for SSDs, particularly random page cost on an SSD is a lot cheaper than it is for a magnetic disk because you're not moving the head or anything, right? So a lot of times you can actually set random page cost quite a bit lower on an SSD. Normally the default is 4. I typically make it 1.1. It's a little more than sequential, but not much, okay? And then also effective I/O concurrency, as you imagine, you can really only send one concurrent or maybe 2 or 3 concurrent requests to a drive. And as it's moving the head, maybe it can hit, a track as it's going. But for an SSD, like there's no moving parts, so you can send a whole bunch of concurrent requests to that SSD and get unbelievable performance. So again, those are 2 settings that we normally recommend if you're using an SSD. And again, these slides are all available. Here's an explanation of the Intel 320. This is kind of an older drive at this point, but again, I think a good example of an enterprise drive with a battery that's really designed for enterprise usage. File systems options, we don't really recommend ext3 too much. ext4, XFS, probably you're going to get the best performance there. You can move the xlog directory to another file system. That can improve things, and you can try turning off ATime if that helps you. The battery-backed unit, I talked about this. Again, sometimes it's on the SSD, sometimes it's on the HBA, but it's really important. Again, it allows for write-back behavior without waiting for data to get to a slower storage area. But if you've got a physical battery, which I'm not sure they even make them anymore, usually now there's supercapacitors. But effectively, it looks this is what the battery looks like, just to give you a visual. The supercapacitors look a little different, but this is actually just a big battery, right? Lithium-ion battery, and I don't know how many are still using this kind of battery, but again, the concept is that you've got some kind of battery keeping the cache durable in that case. Okay. Any questions? Okay. No questions is good? Yes? Okay. Wanted to kind of loop back here and talk a little bit about shared storage, because I know a lot of you are using shared storage. Shared storage is great, right? It's great, it's easy to administer, it's easy to back up, administrators love it, right? But just kind of be aware that there are some downsides. And again, they're typically not a downside if you're storing Word documents or spreadsheets or images on a shared storage NAS or SAN, or typically a SAN, right? It's not that big a deal if you're storing files out there, because the files kind of go when the kernel gets flushed, and we don't wait for fsync, and there's not a lot of throughput of the files. You may be reading them a lot, but you're not churning through files typically like crazy, okay? But because a database is doing that, you've got a contention issue. No matter how many times you want to avoid it, you now have a contended resource. And again, if you're just storing images, who cares how quickly they get to the SAN? But because we're fsyncing all the time, we're going to be waiting for that data to get to the permanent storage. And if somebody else is using that pipe, we're going to have to wait for them to get through before we can get our thing through. I'm not saying don't use it. I'm saying that you have to realize there's a downside. Okay? Most people who care about performance, honestly, are using direct attached storage. Because that's a known quantity, there's no contention, you know exactly what the performance characteristics are, you know exactly what the caching durability is, and you can tune that thing, okay? I'm not saying don't use a SAN, but I'm saying realize there's a problem. I've had another case, we had a customer who had a SAN that was multi-tiered. So you had a SAN, some of it was RAM with a battery, some of it was SSDs, and some of it was magnetic disk. And the data would move from one to the other depending on how frequently it was accessed. Is that a familiar concept to folks? The problem was Postgres would read something. It would go into the kernel cache and the shared buffer cache. It wouldn't be requested from the SAN. The SAN would move it from the battery to the SSD or maybe even to the magnetic disk. All of a sudden, Postgres wanted to write the block, and we got to bring the thing all back in so we can write it, okay? So the customer ended up ditching that whole tiered thing and using the SAN, but dedicating some drives for Postgres. Okay, so just be aware that some of that stuff is assuming a traditional I/O requirement, and databases just aren't traditional I/O requirements. So it's kind of funny to go to a customer, have them touting how cool their hardware is, and then like 6 months later come in and say, remember that cool hardware we told about? Well, we turned off all the features for Postgres because we found it was just, we were getting bad performance. It's kind of funny in my perverse way, I guess. So let's talk about, I've covered RAM, I've covered I/O. Let's talk about RAM, okay? Again, yeah, I've gotten, what did I do? 22 slides just on I/O, okay? I mean, you get the idea, right? Yes, sir?
I had one question about SAN.
Yes.
Is there a requirement for a different size file, maximum size for a SAN then?
So the question is, for a SAN, is there a requirement for different, like, slice sizes or whatever? I've heard people play with like 32K or 1 meg. I've heard different slice sizes. I haven't never seen Some operational people, maybe Peter would have an idea, but I haven't heard any tuning that actually would say what an optimal thing is. Postgres is going to write in 8K pieces, but I'm not sure you have to make your SAN 8K. I think that's probably overkill. Yeah. Other questions? Yes, sir. Okay, so can I comment on EBS and basically cloud storage, right? So the problem with cloud storage traditionally is that it follows the same model that the SAN does, in that it's almost like a big SAN, I mean, technically. So effectively, it's assuming a lot of I/O requests are going to come in. It assumes that nothing's waiting on that I/O request to finish, because normally applications don't wait. Like, you know, when I VI my .profile, like nobody's waiting for that to get to disk, right? It gets kind of trickled into the kernel and then trickled out to the permanent storage, but nobody's waiting for the .profile to be f-synced, right? So basically, when they are tuning the cloud storage, it's kind of the same thing. It's a shared resource. People are all queuing in. Sometimes you get great performance. Sometimes you get terrible performance. Fortunately, I know at least Amazon and I think other ones now have a guaranteed throughput for I/O, and we normally recommend that, because if not, then you basically don't know what your guarantee is. The downside is you'll never get more than that. So there's kind of some interesting thing where when you set that, and I'm trying to remember the term. It was, what's this? Provisioned I/O, right. So when you have provisioned I/Os, that's going to be, you're going to get that all the time, but it's never going to be more than that. But almost for a database server, you almost have to come in with that requirement. Does it cost more? Yes. Is it kind of necessary? Yeah, right. I mean, you can write to an EBS volume, but then it goes away. But even then, it's tricky. Yeah, and because again, SANs just don't work well with Postgres because you've got that wait for the I/O to happen problem. And the same problem you have with the SAN effectively is the same problem you're going to have in the cloud. Yeah. And similar if you're just running VMs in a private cloud. You're going to have the same kind of issue because you've got all these people pummeling into that storage. And a lot of people, when they set things up, they'll be like, OK, I'm going to make this drive just do the database, right? Because I don't want all my other VMs banging on that drive because I know I'm going to be waiting on everything that I send to that, or a lot of the things I send to that. Yeah. Other questions? Yes, sir.
For sequential read, what is the point we should pay attention?
So for sequential read, what is the point you should pay attention? So are you asking like what kind of throughput you should get, or? It's tough because pgtest fsync will give you both an fsync number and a raw throughput number. But I don't really know any numbers off the top of my head that I could recommend for what you should expect from a drive. Because again, if you're Fusion IO or SSD, those are completely different than what you get on magnetic. And then a SAN is going to be completely different as well, depending on which storage layer you hit when you go to it. So it's a little complicated. I'm not sure I have a number off the top of my head. Other questions? Well, I only have 3 more slides, so let's just go through them, and then we'll take the rest of the questions. So, sorry. So RAM. I haven't even talked about CPUs yet. Okay. Technically, I think I have 5 minutes. Is that right? I have 10 minutes. So my clock is 55 minutes? Okay. I didn't know that. Thank you. Great to know. I have 10 minutes. Okay. So I think the first says it all. The more RAM, the better. Okay? Don't put huge amounts of money into your CPU and skimp on RAM. Because by adding more RAM, you're reducing the I/O requirements. Your cache is bigger. You're not having to pull as much from the drive. You're still going to have to fsync. So your writes are still going to have to fsync to permanent storage. But again, having that huge amount of memory reduces a lot of the read load that you typically are going to have to hit with those drives. Ideally, you would have 5 minutes of working set in RAM. How can you compute that? I can't tell you. Even the concept of working set goes back to VMS with DEC, right? I mean, probably even before that. That's when I started playing with working set. But effectively, the idea is that, that you might have a terabyte of data, but you're probably only hitting a small portion of it in a 5-minute period, unless you're running data warehouse. Okay? So the idea is if you can get enough RAM so that 5 minutes of your working set is in there, that's great. That's golden. Okay? But the corollary of that is the more RAM you have, the more possibilities you have of failure of the RAM. And you might think that you live in the, in the rainbow unicorn world, but RAM just fails occasionally. Okay? In fact, they've even done tests where they take a server, they run a workload on sea level, and then they take it up to a mountain, and they run the same workload, and they can see the errors they get by being higher up and not having as much atmosphere to shield the cosmic rays that they're going to hit the RAM. I mean, it's getting that small that you effectively, and if you want to Google that, I think you'll find the study. So the bottom line is any server running a database should be running ECC RAM. Is it more expensive? Yes. Do low-end Intel and AMD servers support ECC? No. You may need to get a higher-end CPU to get ECC support, but I think it's very risky to be running a large memory system and not have ECC RAM. Because not only will ECC report the errors, in a lot of cases it will detect them and correct them at the same time and then give you a report that it did that. The bottom line is that Postgres is only as reliable as the hardware it's running on. If the hardware it's running on is not reliable, Postgres, by definition, cannot be reliable. And that is a serious problem. Okay? And that's where you get corruption. And that's when you get downtime. And that's when the C-level guy visits your office, which is usually not a pleasant thing. I can't speak from personal experience, but I've seen it. Okay? So again, ECC is great. Now we're at the end, right? We're almost done. And I've finally gotten to CPUs. And again, there's a method for that. I did not want to focus on CPUs. I wanted to focus on what I thought was most important for database workload. Once you've got all that stuff lined up, once you've got very efficient I/O, and you've got a durable storage layer that's a durable cache layer, and you've got sufficient RAM to keep 5 minutes of working set, all of a sudden, now your CPUs become important. Now you may actually need faster CPUs because your CPUs are not sitting idle all the time waiting for I/O or waiting for stuff to come into RAM. Okay? So Postgres 9.6 allows you to use multiple CPUs for a variety of workloads. That is going to expand in Postgres 10, Postgres 11. So it's a multi-year process. But again, Postgres is getting better at using multiple CPUs. Okay? If you're using a lot of server-side functions, okay, like triggers, you can generate significant server-side load for that. So I'm not saying the CPU is not important. Particularly if you've got a lot of server-side functions, you may be running a lot of CPU load there, and then CPU can become a bottleneck. Okay? And then finally, CPUs can become a bottleneck if the entire database fits in RAM, so you've got a big enough RAM, so you got 5 minutes of working set, and the workload's read-only, so you're not f-syncing. You're not even having to write a lot. Okay, that's when you're basically getting the CPUs clogged. And when you get a high load average on your server, that's success. I know that sounds really perverse, but when your CPUs are idle and you're feeling the system slow, that's because you don't have enough underneath those CPUs. When you have enough underneath those CPUs, then the CPUs become a bottleneck. Then you can just buy better CPUs, and all of a sudden your system's going to go that much faster. Okay? But you don't want to get into a case where you buy too much CPU and they're all throttled because your lower layers are too slow. And finally, when you're buying quality hardware, buy from somebody who understands databases. That's often really good. So if your hardware person understands databases, they know what type of things to put in. They know that you need a battery on your RAID controller. That person knows what they're doing. Okay? So the bottom line is just because two pieces of hardware are compatible, it doesn't mean they're the same. They don't have the same reliability. They may not have the same performance. Just don't be fooled. Okay? And that concludes what I wanted to say. That is the diagram I want you to think of when you're speccing out hardware. Obviously, I've gone into a lot of details about exactly what you need to do and what things you look for and what tuning you can do to get the best performance out of that hardware layer. And again, once that hardware layer is good, then the next problem is configuring Postgres properly, which again, I didn't cover. And then again, having ideal SQL queries, again, I did not cover. I have 3 minutes for questions, so I'm glad to take those questions, and then we'll finish up. Who has a question? Okay, I will call that success. Oh, yes, sir. I'm sorry, Peter, I couldn't hear that. I'm sorry. Hyperthreading. So hyperthreading, great question. So I have a server with 8 cores. I turned on hyperthreading. You should probably run a test, but most modern CPUs, you should probably turn hyperthreading on. That was not always the case years ago. Hyperthreading would slow down each individual thread. That's in general not true anymore of modern CPUs. So in most cases, you should be turning them on. Hyperthreading should be turned on. Thank you. Good question. I didn't cover that. Other questions? Yes, sir.
What tools do you suggest using to determine where the bottlenecks are in your database?
So what tools do I recommend to determine what the bottlenecks are in your database? The one good one on Linux is IOStat. So IOStat will show you what's happening at the I/O level, and you can actually see the length of the queue in and out of those drives, and you can see the percent utilized. So for example, if I just run, I have a little script, but if I just run IOStat 2, which is a little script I wrote, hold on. Okay, I can actually see, you can see there's my, there's the SSD, and you can see how busy that is, okay? And then another thing you can start to look at is there's a free command in Linux, which will show you how your memory is being utilized, so how much free space you have. Is your RAM feeling constrained, okay? And that's often a good way of looking. And then, of course, in Postgres 9.6, we have a whole bunch of instrumentation that you can enable, which allows you to see wait events. So am I waiting for CPU? Am I waiting for cache misses? These type of things. You can kind of instrument into that area. But you have to get really down into the operating system to kind of to see a lot of this stuff. And it can be frustrating. Other questions? I have 1 minute. Okay, great. Thanks. Have a great rest of the conference.